then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
Okay, greetings, calculus students. Welcome to lesson number 14. All right, lesson 14. A little hard to believe it's only the 14th lesson. Seems like we've been going at this for a year almost. But anyway, lesson 14 is on continuity on an interval. So we have previously talked about continuity at a point. We have actually introduced a theorem, the intermediate value theorem, or IVT, which in the theorem, there's a condition about being continuous on a closed interval, but we never really talked about continuity on an interval. It's a fairly straightforward concept, quite honestly. There are parts of it you can pick and choose. I've been into some heated debates on different aspects, different nuances of continuity with some other calculus teachers through the years. So there's part of it that's somewhat nuanced, but on the surface, it's a fairly vanilla, straightforward concept. So let's look at the agenda for today. So we're first going to begin by reviewing IVT. So I want to go over IVT. There was a couple of questions on yesterday's AP classroom assignment that I saw people missed, and they were IVT problems. So I want to kind of review that, look at a problem like that. And then after we review IVT, we're going to talk about continuity on an open interval and continuity on a closed interval. So let's first revisit the definition of the intermediate value theorem. So the intermediate value theorem states if f is continuous on the closed interval AB and f of A is not equal to f of B, so the y values are different, and k is a number between f and A and f of B, so k is some y value between the two endpoints, then there is at least one number C, an x value in AB, such that f of C equals k. And when we went over this lesson, we kind of demonstrated this from a graphical standpoint, so you kind of understand it. What I'm here to reinforce is, and I talked about this when we did the lesson, is the conditions that I need to be able to utilize or apply IVT. And that condition is the function must be continuous on the closed interval. That is the important condition. I spoke of a little bit later, we're going to be doing EVT and MVT and Rowe's theorem as well. Again, EVT is extreme value theorem. MVT is the mean value theorem. Mean value theorem will be the most important theorem we do of this set of theorems. But the deal with them is understanding their conditions in terms of continuity and differentiability. So those are the two important conditions to understand. It's also important to understand because, it's part of the definition, and everything in there, as we always say, is important. So it's very important to understand that f of A is not equal to A and B, and that C is in between A and B, and K is between f of A and f of B. All that's important. But the most standing condition that needs to be understood is that the function is continuous on the closed interval. So when we encounter problems such as this, so here's a problem similar to a problem you saw in AP classroom. Let me just read the problem. It states the table above gives values of a function f as selected values of x. Which of the following statements, if true, would be sufficient to conclude that there exists a number k in the interval from 1 to 9 such that f of k equals 15? Now, again, you have to think about the things that you have learned where such a statement as there exists a number k in the interval of 1 to 9 such that f of k equals 15 would relate to. And that should only be the intermediate value theorem. It's an existence theorem. And this is talking about there exists a number k, and that's what it gives us. And this number k is in the interval from 1 to 9. That's the interval of my x values. And f of k is 15. That's a number between -6 and 24, which are my two endpoints of my y values. And by the way, when we do IVT with the table of values, it doesn't have to be with the endpoints. For instance, IVT guarantees that there's at least one number between 3 and 4, such that f of that number is choose any number between 11 and 20. So customarily, we tend to use the endpoints, but it doesn't necessarily have to be the endpoints. So once you understand that this is an intermediate value theorem, all the other parts of the theorem have been met. The fact that the number is between the x values and that this y value is between the two y values. The only condition that we need is that the function needs to be continuous on the interval from 1 to 9. That is it. That's the answer. There's nothing else that is relevant. The fact that the function is defined means nothing. The function can be defined on all x values, but can be not continuous. A graphical example of this. So let's say this is the point 1, -6, and say up here, this is 1, -6, and up here is the point 9, 24, and this is -6, this is 24, so say this line is 15. Now, I can have a function that's defined on every x value I have, and it doesn't necessarily have to be that a value equals 15. For instance, here's a function that's going to be defined on every value from 1 to 9. So here's a function. I graph it. I can make it a little interesting. I'm going to get right here on 15. I'm going to have an open circle, and then I'll have a closed circle somewhere else. And then I'll continue. And there's just one example. So this function here is defined on every value. So whatever value this is, well, we're going to say this is the value when x equals k. X equals k is defined. F of k is defined. It's right there. So every value is defined. But just being defined is not enough to guarantee you're going to cross this intermediate value. Again, intermediate just means between these two values. Just being defined is not enough. You have to be continuous. Just being defined is not enough. You have to be continuous. Let's look at the other answer choices and why they're not sufficient. Again, the word used there was sufficient. And answer choice 2 says the function is increasing on all x values in the interval from 1 to 9. And that's one that gets a lot of people, that guy that's increasing. And in fact, some people assume because these numbers are increasing and these are just finites, these are just selected values, that the whole function is increasing, and we can't guarantee that. But even if we can say that the function is just increasing for all values on the interval, once again, it doesn't guarantee that we're going to cross that intermediate value. And I can use basically the same graph I just looked at. So let's say I have a jump discontinuity, and then I go and I increase. So here is a function that is increasing on all values, but yet does not cross the intermediate value. So increasing is not enough. Again, the theorem doesn't say the function has to be increasing. The theorem doesn't say the function has to just be defined. The theorem states that the function must be continuous. And Roman numeral 3 is just one I threw in just to kind of solidify the point. And Roman numeral 3 again says that the limit exists for all x in the interval. And everyone understands that the limit can exist at a point, but you not be continuous at that point. And if you're not continuous at the point, then there's a possibility that you won't pass through that intermediate value theorem. So whenever we encounter this problem dealing with IVT, the condition that must be there is that the function must be continuous on the closed interval. Okay, so hopefully we put that guy to bed. Now let's go ahead and look at, well, let's review the definition of being continuous at a point. Something you should know. I want to just review it real quick. So there's the definition of being continuous at a point. The function is defined at the point. The limit as x goes to the point exists, and those two things are equal. So then what does it mean to be continuous on an interval? So first I'm going to look at an open interval. So an open interval just means I don't include the endpoints. So the endpoints are not included. And it's a very elementary, rudimentary definition. So if I'm continuous on an open interval AB, a function is continuous on an open interval AB when the function is continuous at each point in the interval. Makes sense, right? So here's just a graphical example. So here's some graph. And as long as I'm continuous on every point in this interval, then I'm continuous on that whole open interval. But now again, this is an open interval this guy is dealing with. Now, what do you think it would be if it's a closed interval? And previously I alluded to some hot debates I've been in the past with other calculus teachers. And it all stems from misconstruing continuity on the closed interval with continuity on an open interval. So before I even address the definition of continuity on a closed interval, let's see what we think about continuity on the closed interval. So I'm just going to take the same graph and include the endpoints. And so I'm talking about being continuous from A to B, including A and B. So here's a question to think about. Would the same definition hold? Meaning, to be continuous, can I just be continuous on every point in the interval? I want you to think very carefully about that. Would it be sufficient for continuity on a closed interval to be continuous at every point in the interval? And hopefully you're saying no. And the reason is the endpoints. Because you can't be continuous at these endpoints. Why? What does it mean to be continuous? Okay, the function is defined at the point. Okay, f of b is definitely defined. What else? The limit exists. Does the limit exist at b? This is an endpoint. Does the left-hand limit equal the right-hand limit? Oh, it doesn't even have a right-hand limit. There's nothing on the right-hand side. So this limit doesn't exist at b. So this limit doesn't exist at a. So I can't say it's continuous at every point in the interval because a and b are included in the interval and the limit doesn't exist on a and b. So how does the definition take that into account? Because the only thing we can look at on a and b are one-sided limits. I can only look at b from the left and I can only look at a from the right. And guess what? That's how we define continuity on a closed interval. So continuity on a closed interval, a function is continuous on a closed interval AB. And again, closed interval just means we're including those endpoints when the function is continuous on the open interval AB. So meaning the function is continuous on every point in the interval except for A and B, and the limit from the right of A equals f of a, and the limit from the left of b equals f of b. So that's the difference between continuity on the closed interval versus continuity on an open interval. Open interval, you're just continuous on every point in the interval. Closed interval, you can't say you're continuous at every point in the interval because that that includes the endpoints, and the endpoints you can't be continuous because you're only going to have one side of the limit. And so that's why we have these one-sided limits added on to the definition. Okay, before we look at some problems, I want to list 6 functions which are well behaved, if you will. These are functions which are continuous on their domain. We've talked about two prior, which are polynomial and trigonometric functions. We're now going to expand our list. And so these six functions are continuous on their domains. And these are polynomial functions, trigonometric, rational, radical, exponential, and logarithmic. And though we haven't done a lot with the last three yet, most of the functions we've been doing thus far have been polynomials or rational. And when I say a rational function, I'm talking about a function with a polynomial, a ratio of polynomials. So the numerators are polynomial, the denominators are polynomial. So radical, of course, are functions like a square root, fourth root, functions with roots. Exponential are functions where it's some constant raised to the power of x. And I believe you understand what a logarithm is. So this is something to study. Of the many things that you need to study is that these particular functions are continuous on their domain. Now, these particular functions are continuous on their domain. It doesn't mean that these functions can have discontinuities, because you know rational functions have discontinuities. And you may not know, but 4 of the 6 trigonometric functions have infinitely many discontinuities. So a function can have discontinuities, but what separates it for these functions is that the discontinuity is not in their domain, which means if we can figure out the domain of these functions, which we can, something you've been doing since algebra 2 and maybe even algebra 1, then you know everywhere the function is continuous. And sometimes that's pretty important to determine everywhere a particular function is continuous. Now, I want to make an example with rational functions, since those have been our kind of go-to functions, and kind of explain what we mean by these functions are continuous on their domains. Okay, so let's say we're given the following situation. So I have this function f of x, and it's asking me to find all intervals where f of x is continuous. And that could seem like a very daunting task, especially if maybe I'm not familiar with the graph of f of x, and we're talking about an infinite number of numbers. How can I figure it out? But again, if I understand those 6 functions, those 6 well-behaved functions, which are continuous on their domains, they're not continuous from negative infinity to infinity. They're continuous on their domains. Well, polynomials are continuous from negative infinity to infinity. And sine and cosine of the 6 trigonometric functions are, but those functions also, their domains are negative infinity to infinity. But that's a side story. But the deal with these functions is that they're continuous on their domain. So if I want to find all the intervals where the functions are continuous, all I have to do is find the domain of those functions. So for instance, this function, and this goes back to stuff you did in algebra 2 and pre-cal, to find its domain, it's a rational function, so it's going to be all the values of x except the values which make my denominator 0. So I know my denominator can't be 0, so x cannot be 2. And so the domain is all real numbers except for 2. So the intervals of continuity are all real numbers except for 2. So that would be negative infinity to 2 union 2 to infinity. So the moral of the story is whenever they ask you where a function is continuous, or to name all the intervals in which a function is continuous, and it's one of our 6 well-behaved functions, all you have to do is find the domain of that function. Now, I know you know how to find domains of rational functions. Of course, the domain of polynomial functions are all real numbers. A couple of the trig functions are all real numbers. Then a couple of the trig functions have infinitely many discontinuities. So right now, you don't really have that understanding of those trig functions that have those discontinuities. So we're not going to ask you about that just yet, but you do know how to deal with the polynomial functions. If I just gave you any polynomial and asked you to find all the intervals where it's continuous, of course, you're going to say negative infinity to infinity. In fact, if I gave you an exponential function and asked you where it's continuous, you're going to say negative infinity to infinity. Logarithms, there's restrictions that we'll look at a little bit later. and also 4 of the 6 trigonometric functions. There are also restrictions that we're going to look at later. Now, I want to show you graphically like how this looks where a function is continuous on its domain. So a function has a discontinuity, but that discontinuity is not in its domain. So if you look at this, function from an analytical standpoint, if I was to factor this numerator here, that would be x plus 9 times x minus 2. And I have x minus 2 on the bottom, so the x minus 2 would cancel. So that means this function is pretty much the same as x plus 9, except where x equals 2. And when x equals 2, x plus 9 is 11, but when x equals 2, f of 2 is undefined. So as you know, what that means is the graph of this guy, so let's just say that's 9, has a y-intercept of 9, a slope of 1. The graph of this guy, where is it undefined at? It's undefined at 2. So let's say that's 2, 10, 11. And so let's say that's 11. So the graph of this guy looks something like that, of course. Now, again, we see a discontinuity, but however, that discontinuity is not in this function's domain because the function's domain is every number except for 2. So it's continuous on its domain. Well, how does a function look that's not continuous on its domain? And I can easily illustrate what that means for a function that's not continuous on its domain. So let me go back to our first one we looked at. So this function has a discontinuity at x equals 2, but x equals 2 is not in the domain of this function. So this function is continuous on its domain. But what if I did this? Now the function's domain is all real numbers. It's defined at every value from negative infinity to infinity, but yet it has a discontinuity right there. So this is just one example. I mean, there's several I could provide, but this is just one example of a function which is not continuous on its domain, because again, this graph, the domain is negative infinity to infinity. It's defined for all x values, but it has a discontinuity. And if you notice, one way I can get a graph like this is with a piecewise function. And you may have noticed that piecewise functions didn't make our list of 6 of the well-behaved functions. And our list of 6 is not all the functions that behave nicely like this, but it's a list of the main functions we're going to be dealing with. It's the list of the functions we mainly deal with as we get deep into the course. Okay, so that's going to conclude the lesson. And the only new question I'm going to be asking of you now is I'm going to give you a function that you can handle, and I'm going to ask you to find all the intervals in which the function is continuous. And I may also ask some little tricky questions dealing with continuity. But that's our continuity lesson, continuity on an interval lesson, and we'll see you next time.